Assalamualaikum and hi everyone. We have discussed on the MOSFET gate structure that resembles a capacitor. From now, we are going to apply that knowledge to discuss the MOSFET under equilibrium condition. The gate structure of a MOSFET can be represented by capacitor. At equilibrium, due to the constant leveling of Fermi level throughout the system, band bending happens at the silicon dioxide and silicon interface of the substrate part, which results in band bending. This band bending creates a built-in voltage and depletion region. Since the surface at the silicon dioxide-silicon interface is depleted of majority carriers, and as can be seen in the enlarged figure, Fermi level is higher than intrinsic Fermi level, EI. This layer at the interface is effectively N-type, which forms a channel. However, this channel has very low conductance because only very few electrons exist. So, the discussion of MOS capacitor, we're focusing on the gate structure. In this subsection, we further add the source and drain to the discussion to talk about the qualitative analysis of MOSFET at equilibrium. A common connection for MOSFET operation is to have the source tied to substrate and connected to ground while VGS and VDS are varied. Same to as what we have learned from MOS capacitor, VGS controls the formation of the channel. In MOSFET, we have the VDS that controls the flow of current along the channel from source to drain. As seen earlier, in equilibrium, band bending happens, thus causing the surface to be depleted or inverted even when there is no bias applied, meaning that channel exists at equilibrium. The substrate doping can control the channel behavior in equilibrium. It can control whether the channel is strong enough or not to be considered as a proper channel ready for current flow. I have shown this before. This is a schematic diagram of an N-type MOSFET or NFET. Please note the important dimensions in MOSFET. The position of these dimensions are fixed. W is the width of the channel. Length of the channel is represented by L, and TOX is the oxide thickness. From the schematic diagram, we can see that there is no channel between source and drain at equilibrium. At equilibrium, as can be seen from this Venn diagram, Fermi level or EF is close to the intrinsic level EI and slightly cross the EI at the silicon dioxide and silicon interface. This shows that a channel does exist. However, the channel has low conductance because there's only very few electrons exist. Due to low electrons concentration, even if we apply the source to drain voltage or VDS, only a very small current can flow. This device is said to be in sub-threshold region. There are two types of current voltage characteristics of MOSFET. One is transfer curve and this one is output characteristic. In both IV curves, sub-threshold region can be seen. In the transfer curve, the sub-threshold region is this region, where VGS is lower than VT, and at output characteristic, the region is at the x-axis. In both cases, IDS is considered very small or zero. In the MOS capacitor discussion, we used the Venn diagram that was drawn along the A' line at the gate structure. The Venn diagram includes the energy levels of gate, outside layer, and substrate. This Venn diagram is suitable to discuss the mechanism of gate voltage VGS without the effect of VDS because source and drain are not stated in the Venn diagram. To include source and drain, especially to discuss the effect of drain source voltage, the cross-section along the B' line are drawn, which is called the energy barrier or EB diagram. This diagram shows the conduction band of the materials at source, channel, and drain. Although the substrate is a p-type, the channel region is effectively n-type, but the electron concentration is very low. Thus, if we draw the constant Fermi level here, the conduction bands at source and drain are overlapping with EF because they are degenerate N+ material. But at the channel, the conduction band is further above EF. Thus, this creates an energy barrier EB here. From the MOS capacitor band diagram, due to the band bending at equilibrium, an effectively n-type channel exists. In the EB diagram, since the conduction band of the channel is higher than those for the source and drain, there is a barrier at source and drain, and the barrier is high. The high barrier only allows small amount of electron to be at the channel. Although the source is extremely highly doped with N+, but the channel is only weakly n-type. Thus, very few electrons are in the channel and the conductance are very low. It is so low that the channel conductivity is negligible that if the drain to source voltage VDS is applied, only a minuscule current can flow. At this point, the device is said to be in subthreshold region. In summary, there are two types of band diagram for MOSFET. One is the band diagram of the gate structure drawn through A prime line, and another is the EB diagram. Due to the band bending, although channel exists at equilibrium, the conductivity is negligible, and there are only very few carriers at the channel. Voltage at the gate, or VGS, will affect conductance of the channel. VGS controls the formation of the channel, while the drain to source voltage VDS controls the flow of the current along the channel from source to drain.